So we're going to talk about the sequence of tests that we're going to do today. We're not going to do just one test. We've got quite a few here to do. So we're going to start out with the swept sign test. And that's where we're going to actually vary the input frequency on the shaker table, starting at 5 Hertz, and we're going to sweep it up to 2,000 Hertz, and that will be done over a period of 2 minutes. So that's what we're going to watch. When we do this swept sign test, we're going to first conduct it on an aluminum beam, and we're calling it short because there are longer beams that we have in the lab that we can use, but we're calling this the short beam. That's the 11-inch long beam. Note, by the way, that the L in this formula that you're going to be using here is 11 inches. That's the free length of the beam. So we're going to do the aluminum short beam, and then we're going to rotate it 45 degrees relative to the direction of the input vibration, because we want to see what the sensitivity is in terms of measuring resonance if we orient the beam differently. That's going to be an interesting finding. And then finally, we're going to swap out the aluminum beam with a titanium beam oriented in the same position as case number 1, the aluminum beam. Right? So we're only just looking at the material differences here, and here we're looking at the change in orientation. Now finally, we have a deflection test that we're going to do, and that is without using the shaker table at all. We're going to take the beam, and it'll be a different beam, actually an aluminum beam. We're calling it a long one because the length is longer. And we're going to deflect it manually and let it go in a flick test. And we'll watch it rock back and forth very, very quickly. And the accelerometer is going to pick up that data. And if we can take that accelerometer data and integrate it in time, we can get a plot of velocity versus time based on the accelerometer data. And then if we further integrate that data in time, we can get a plot of position versus time. And so from that position versus time data, we're going to be able to estimate how much the beam deflected. And we're going to compare that against the measurement that we're going to take in the test. So next, what I want to talk about is the data that we're going to be pulling in and the way it's displayed on the control computer. So let's take a look. So if we look at the screen here, this is a display showing primarily the control line input. And the control line here is the center blue line. We're trying to control it in a profile that looks like this. On the vertical axis, we're controlling acceleration, and on the horizontal axis, we're controlling input frequency. Now these are input frequencies and accelerations on the vibe table. When we start out the test, the shaker table will be searching to start at 5 Hertz, 1/10 of a G acceleration. And then we're going to ramp up in frequency and in acceleration until we get up to a point here where we're at 1 G of input acceleration, and that happens at about 18 or 19 Hertz. And then we're going to hold acceleration constant and steadily increase frequency from that point all the way out to the end of the test at 2,000 Hertz. And that should occur about 2 minutes after we start the measurements. All 4 channels will be recorded at the same time, and we'll be able to hand you that data in an Excel file. And the format of that data will be time in seconds versus acceleration in Gs over a period of time. So we'll get that for all 4 channels, and then you can use that to manipulate your data and post-process and analyze.